All right, this is a continuation of our operating system lecture. This is a discussion, and we're continuing. If you remember our previous application, we had this wonderful bike computer device where it was recording wheel rotation, a mode button, and then the internal clock associated with the tick of every second as it went along. The only output was an LCD. You've seen this where we have done a identification of the state machine. And in this case, our state machine is nothing more than 3 ISRs with a main program which will run when you reset. So this is the idle state right here. And then these will be what happens. Now, remember I mentioned when the wheel rotates, we do a little bit of computation, but we never actually do anything with the LCD. The only time we do anything with the LCD, guys, the only time we do anything with the LCD is when the time of day counter ticks to a new second, and then in that case, you actually display things on the LCD. For example, the speed that you're running at may be a little bit slower, or maybe a little bit faster, depending on what's happened in the last second. So, the limitations of doing a exclusive event trigger using interrupts is that everything is being done within the ISR. And since all the code is in the ISR, it makes them long, and you could have some trouble if you are in an ISR and something else needs to interrupt and you don't allow it. Remember how I mentioned in the concept of interrupts, you could actually disable interrupts altogether. And the interrupt may be very important, but you don't open it up and get to it because it is being masked and it's not allowed to operate. So the difference, or maybe a combination of these two, is what we call round robin with interrupts. And so what you can do is you can have an interrupt handler that if it comes along, it'll actually say, now it is time to service me. And so that's what this line right here says, is that when an interrupt for device A occurs, all it does is it sets a flag. Then within a larger loop, then it says, oh yeah, if the device A is supposed to be worked on, then do it and finish it. Then it will give device B the opportunity to go ahead and do it. Then device C, if there's something there, then do it. Again, the problem is if any one of these activities take an excessively long amount of time, notice that this interrupt doesn't allow something else to process immediately. You still have device A finishes its computation, device B, and device C. But this time it's not in the interrupt. It is in the main program. That means that everything is a single priority. But if you want more than one priority level, then you're going to have multiple interrupt priorities possible. And you'll have to put that in the main code. So maybe in the main code, you'll have different loops that will run depending on if it's the highest priority versus the lowest priority. Now, again, one of the biggest problems that we had from that earlier, remember that earlier example that we had where you had the possibility of the video processing taking an awful lot of time and not allowing the audio to be handled. And if you remember correctly, the audio had to be handled every 20 milliseconds, and one of the video jobs took 27 milliseconds to run. So it seems like it would be nice to have the best of both worlds. Excuse me. Where perhaps you could have an effort done and still allow other things to happen. Like here's compressed frame. Maybe you could have that in a separate little functionality so it can get done. Well, again, the problem with this is that this compressed audio, you want to actually interrupt and have it execute. Or I'm sorry, while the compressed frame is running, remember that took 27 milliseconds, you want this entire function, or I should say these functions right here, to execute and then return back to compressed frame. So obviously you need to do something else, otherwise this truly won't work. This is specific detail about that. I don't think I'm going to go into it. I don't think I have much time to handle this as well. So what I want to do is I want to talk briefly about scheduling, and this is going to be something that will be helpful for your homework assignment coming up. So you see the reactive systems. In other words, activities are done based on interrupts. That was the example of the bike computer. You also saw schedule activities where everybody gets a little bit of time. And the operating system will schedule these tasks that may or may not be identified by interrupts. But again, scheduling is such that you schedule activities only when they're needed. And you can do that by interrupts, or you could have the operating system always poll and give them a chance to do something. Let's look at one example higher up. At least a higher up version. We're not going to look at code yet. Well, here's some rules. We're going to define certain functions to be the tasks. In other words, a C function will be a task that, in one case, will allow to run to completion. And if there's a task that wants to run and that is ready to run, then it runs. And here's an interesting one. This will change depending on what your scheduler is based on. But in our example, we will finish a task before we start another one. Remember, there was a problem with the video compression. It would run 27 milliseconds and would not allow the audio to be done. This still will not allow it to run. And if there's more than one task to run the highest priority. That's again if there are two tasks ready to run at the same time, and you're given a choice between the two. We'll call this our round robin in a simple example. So, let's take this example. In this, what happened there? That was interesting. Just by pushing this forward, going forward and back, all right. So, we have tasks 1, 2, and 3. These are different priorities. Which one has a higher priority? Well, the way we're going to work this is that the lower number priority is the one that has precedence to run over the other. So in this case, we're going to identify task 2 and 3 can start at the same time, but of course only one could run at a time. So we take the one that has the highest priority. This says priority 1, task 2 would run first. This is the amount of time it takes. If each timer tick is, let's say, 1 millisecond, what we're saying is that the task here is going to take 1 millisecond, 2 milliseconds, and 1 millisecond. Or you can just identify the elapsed time based on not necessarily clock time, meaning milliseconds, but meaning approximately what sort of time is associated with each of these timer ticks. Next, or finally, is the frequency at which these run. So I need to run task 3 every 5 of these timer ticks. I need to run task 2 once every 10, and I need to run task 1 once every 20. So just looking at this with the frequency of task 2 and 3 and the length of time it executes, how much time is going to be spent running task 2 versus task 3? Is it going to happen? Which one will take up more time in the long run? All right? The answer is same time. Because in the time of 10 ticks, 10 of these time ticks, it'll be running twice. And in the frequency of this, every 10 timer ticks, it'll run twice. For two of those time ticks. So let's take a look. First thing we do is we start out and we say, all right, we're going to have a counter. This counter right here will be first preloaded with this frequency. And every timer tick, we will decrement all of these frequencies. So every timer tick, you're going to go from 20 to 19 to 18 to 17, all the way down to 0. And when it ticks over from 1 to 0, what it does is it sets this variable here, run, which is a binary, to 1, meaning go ahead and run. So if you look here, time number 3, we set it at 5. It counts down to 4, to 3, to 2, to 1. And when it counts down to 0, it says, yes, we will put 1 here in this binary variable. And then we'll reset this to its original frequency. So then, 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, to 0, then it gets reset to 5. 4, 3, 2, 1, etc., etc. Anytime you see a 1 here, then you take a look at the priority. If there are two things that have the same priority, that have their run bit set at the same time, you take the priority task. So look at this case right here. It just so happens that all of them are scheduled to run. And if you look at the priority, we'll run task 2, followed by 3, followed by 1. So here we run 2, then we'll run 1. Oh, sorry. Task 2, then task 1, then task 3. Task 3 is the lowest priority. So we'll run 2, then we'll run 1, then we'll run 3. Notice one problem here at the end. There's only 2 time ticks between when it first runs and the next time it runs. And oh, notice this, that it goes 1, 2, 3, 4, 5, 6, 7, 8 time ticks between 2 times here when it runs. And in fact, right here is 1, 2, 3, 4, 5, 6, 7. 7 time ticks between these 2 when it runs, and 3 right here. But on the average, since this is a fairly unloaded system, most everything, in fact, this is the worst case, most everything will run, but some may be late. But that's okay in most cases, because in real-time systems, very often you don't need things done immediately, you need it to be done fairly close. If it needs to be run immediately, then it needs to be what's called a hard real-time task. So this is lightly loaded. Let's take a look at this next example. We've now added another task. Task number 4 with 0 priority, which means it has the highest priority. And look at this, it runs really often. So in this case, again, we count down 3, 2, 1, 3, 2, 1, 3, 2, 1. Anytime you see a 1 here, I've gone ahead and I've bolded it to make it look obvious when it was first set to 1. So notice in most cases, it's set to 1 and it's able to be executed immediately. Oh, but look at this case. 3 is set and it's not able to get run for how many times? Well, let's see. 1, 2, 3. It's finally able to do it the 3rd time. But here is the worst case. It's supposed to do it every 5. 1, 2, 3, 4, 5. So here it finally gets to run, but at this time, notice that right here, it already counted down to 0 already. So it missed 1 execution of task T3. And if you look at this situation right here, where task 1 finally gets to run, whole bunch of things are running right now. This is nearly a completely utilized system. There's a lot of, once the system gets going, it's going to look more like from here on, actually starting right here at 20, 25. This is about when it's going to, there's going to be a couple open spots here and there, but it's going to be nearly full utilization. And this is when you can also look at how the functionality of the system runs, because there you go, this is a fully overextended system. You are missing things continuously. In this case, how many times does T3 run from time 0 to time 30? We would expect it to be scheduled and to run how many times? 5 or 6, right? In this case, it only ran 3. And in many cases, notice task 4 is taking an awful lot of time to run. And it's predominantly, or it's taking over a lot of the time of the processor. So, if you were designing an embedded system, what would you do in this case? Make it into a hardware process. In other words, maybe introduce another microcontroller that would handle that one, right? Or what's another trick? What does this here represent? Time, correct? Can you change time? In a microcontroller, can you change time? And how do you change time in a microcontroller? Speak louder.
Extending cycles.
Extending cycles? There's an easier way.
The clock frequency is made less.
All right? Increase the clock speed. And if your current part doesn't work at that clock speed, you can always buy, almost always, a drop-in solution for that one part that runs a little bit faster, or 2 times faster. Now, is that going to cost you more money? Yes. But in many cases, remember the amount of time that this takes to run here is going to be reduced. Let's say if you double the clock, these tasks will take half the time. And, oh, by the way, these are just timer ticks. They're not necessarily milliseconds, it's a certain frequency. So this would pretty much stay the same. And what you would see here is that the length of time that it would operate is now cut in half. All right? So, what I would like you to do is to take a look at the first 10 seconds or 10 timer ticks of this. And between you and your neighbor, draw out this clock and tell me what this clock would look like if the time of these were half. All right? So let's pause. All right, we're back from the 10th of this exercise, and we had enough people say that they needed a little bit of help. Sorry for the extra points. All right, so there's 2 important changes to this. Number 1, everything here is changed from the table that you saw in slide 19. Slide 19, right? By the way, guys, camera picks up all the talking, so I know you're excited about this. Nothing's going to change across this way, so that will turn out to be 19, 18, 17, 16, 15, 14, 13, 12, 11, 10, 9. I added time 11 here just because it's interesting. 9, 8, 7, 6, 5, 4, 3, 2, 1. By the way, this goes to 10. And at this point, I can remember that, oh yeah, I'm going to have the run right there. This is going to take every 5, 4, 3, 2, 1, 5. how long, the entire time here. So this will be T4, taken up by this space. Interesting enough, it has been addressed, so we reset this counter to 0. Actually, once it starts to run, it gets reset to 0. And there's nothing in T4. In T5, there's nothing else to run. So at this time 5, task number 3 takes half of this time. Interesting enough. And then at this time, T4. T4 will take this entire time. Nothing else goes on until this time, where it's T4, it takes the entire amount of time, right? And at this time, we have 2 and 3 executing at the same time. Which one has higher priority? 2 has higher priority. So T2 will take the entire time of one of these timer ticks. And since we didn't get the time 3, it will still have 1 in the run column, and it will take up half of this time. So that will give you an example of what happens if you increase the microprocessor clock. But remember, these are tasks that are really concerned with the wall clock. So yeah, it still takes a frequency of 20 timer ticks. And the timer tick will stay the same. In this case, we'll say it's 1 millisecond. So if your microprocessor is running at 50 megahertz, and this timer tick is 1 millisecond, if your microprocessor now runs at 100 megahertz, this timer tick would still be set at 1 millisecond, because it's the task that has to be done at a certain frequency. And the frequency is based on real time, the time of the world, not the time of the processor. So as you can imagine, if you had a microcontroller that's running at 25 megahertz, that would be really bad. But if you could run it at 100 megahertz or even 200 megahertz, then you could get a whole lot more, or you could ensure that you don't have a lot of tasks that would conflict with each other. All right, let's continue on. So you never know when an exercise like that will show up on a quiz, or on an exam, or on homework. 10, 10, 10, 10, 10. So, this is what's considered a run-to-completion scheduler. So a run-to-completion scheduler will run certain tasks at, as I said, a certain frequency, and the frequency is based on milliseconds. And it doesn't matter how fast your microcontroller clock is. So that table that I showed you stored information associated with how many ticks between each task release. We also saw the release time, and there was a little Boolean counter there to let you know when a task is ready to run immediately. And this round-robin scheduler will be in a main loop in a while loop, so it will run forever and ever and ever and ever. Now, the way we work this is that a periodic timer. So in this case, I declared this to be 1 millisecond, for example, right? That's 1 millisecond, the amount of time from here to there. So I declare that to be a specific time, and I will set it up with a timer. And the timer will generate an interrupt every 1 millisecond. So every 1 millisecond, the interrupt service routine will take a look at my schedule table. Now, what are the things that actually were important from this? What do you think the interrupt service routine would affect here? Do you think the interrupt service routine would schedule the task? Usually you want to keep tasks out of it, or execution out of interrupt service routine. But what is an interrupt service routine really good for? Not computation, but setting flags, setting variables. So in this case, what's a variable that changes? Well, right here. This run is something that can be changed, and something that's really simple is decrementing going from 18 to 17. So you'd expect in your interrupt service routine, something would go through each one of the tasks and say, is it ready to run yet? And the way it knows that is by continually decrementing. So at this time right here, when you're going from 19 to 20, the interrupt service routine would run, and it would say, oh, look at this, task 1 just went from 1 to 0. So I'll reset this number at 20, and I'll set the run bit. And oh, look at this, task 2 has gone from 1 to 0. So I'll reset this to the frequency, and I'll set the run bit. Oh, look, task number 3 went from 1 to 0. So I'll reset task 3, and then I'll set the run bit. Task 4 went from 2 to 1, it's not time to run yet. And then the interrupt service routine would exit. So what would you expect would be running as it goes out of the interrupt service routine? It's the big super loop that says, is it time for task 1 to run? How about 2? How about 3? And so what you'll see is, again, in the interrupt service routine, when time reaches 0, you set the run flag. Now the interesting thing is that this is a run to completion model, which means that each one of these tasks has to complete before the next one can run. And that's important to note, that it must run to completion. So in the example that I showed here, or I'll even make it show this example up here. So in this example, let me find a good one, right here. Notice that task 2 is running, and it takes 2 timer ticks to run. But at this time, number 21, it determined that it's time for task 4 to run. Task 4 is a higher priority over everything else. Does task 4 start running right away? No, because it is a complete or a run to completion scheduling system. Task 2 must finish executing before task 4 is allowed to run. And notice that even though task 4 was scheduled to run after task 1 and 3, it has the highest priority of any of them. So it allows task 2 to complete running, and then it will run task 4, even though task 1 and 3 ask to be serviced first. And again, priority is determined by the position in the table. So, what we're going to do is, let's see if we can find this. We are going to create an application programming interface that will run this whole thing. And you never know when something like this will show up on a test or a lab. So we're going to have these specific functions that you can call. These specific functions are add task, remove task, run the real-time scheduler, which you only really call once, enable task and disable task, and reschedule the task. And these are pretty typical if you are going to be using an operating system where usually a task has a certain life and you start it and end it when it needs to start and it needs to end. So for example, in your mobile phone, usually you have a task that says, all right, sort the phone book for the specific user. And it only runs how often? Whenever you change the phone book, right? And do you ever want to run that sorting of the phone book when you're taking a call? Probably not, because probably taking the call and handling the call takes so much more time or it is more important than sorting your address book. And so the operating system would schedule the sorting of the phone book only after you changed it and while nothing else important was going on. So in that case, it would add the task of sorting it, and when it was all done, it would just remove that task from ever being, having to be done, because it already has been completed. And that's in an operating system where tasks are added and taken away. Again, in the adding of the task, you identify the specific address of the function. In other words, you're going to go to a certain place in memory and run it, how much time it needs to, or how often it needs to run, and then its priority compared to everybody else. Moving task, you only have to worry about the task. Running task, only worry about the task number. And again, some other functionality that we'll see a little bit later on. What I would like you to do is to go through the specific notes in the online and read about this, because we're going to go over this in a little bit of detail, or quite a bit of detail, in the next class. Thank you very much.
Now we're good.
All right, welcome to Embedded Systems. What I'm going to cover right now is a quick assessment on the solution for this. So I do have to apologize in advance. I didn't realize that one of these problems would be a lot harder than the other. Let's see just how much harder it is. This is very similar to what's in the there we go. Very similar to what's in the book. All right, guys, if you can make sure to be quiet so the camera doesn't mix with your voices. Gentlemen? Ladies, gentlemen? All right, so is this thing on? Hello, McFly. All right, so remember, you're supposed to watch Back to the Future. That's one of the assignments for this class. One thing that we know about solving this problem is that A is called how many times? Every 2 timer ticks, right? B is called every how many timer ticks? 4. C is called how many timer ticks? 5. So that means I could look at these and immediately I could identify what all the values will be before I even look at what's going to run. So I know this is going to go from 2 to 1 to 0, which will then be reset to 2 to 1, 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 2 to 1, 2. Right? This is at 3, so at the next timer tick it goes to 2 to 1, and then it starts at 4. 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1. Easy enough, right? This one right here, it's at 1, so it ticks down to 0, then it gets reset to 5, 4, 3, 2, 1, 5, 4, 3, 2, 1, 5, 4, 3, 2. So that's all done really easily, right? It's always enabled. I don't say I'm ever disabling anything, do I? So these will all be 1. Boy, that's kind of easy, isn't it? And here's the other last easy assessment to make. Anytime I go from 1 to 0 and then it gets reset, I always set the run bit, right? So I always know that when I go there, that run bit will be set there, 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 there. Always be set, right? Same thing here. Always set there when I go down to 4, 3, 2, 1, 0, there. And then again, at this point here, here, here. So, the only thing I have left is what will actually run. So what I've done so far is I've shown what will be computed in the interrupt service routine that occurs every time you get a timer tick. The funny thing is, it really doesn't matter how much real time it takes. What does matter is that each job takes how many timer ticks? 2.5 timer ticks worth of time. So, let's look at how often things are going to be going on. Well, if it's 0, in this time frame, that will remain 0, this will remain 0. This says run. So what's going to run during this time? C. And C will take how much time? 2.5, right? So you can assume that this is going to be the time that C executes. Oh, by the way, if you start to execute, it's going to be set to 0, and it will remain 0 until it gets set to 1. So in time number 2, oh yeah, it hasn't been set there. So at this point in time, C will complete running, somewhere in the middle of this. So what will run next? The priority for these are priority 0, priority 1, and priority 2, right? So the next thing that will run is 2. Well, 2 is set to run again, because it hasn't been moved. So at this point, A is going to take 2.5 times, right? So this is A. Now, interesting enough, A has been set, and it's set again here. And B doesn't get a chance to run, so the run bit is still set. At this point, A hasn't been able to run again, B hasn't been able to run again, so that's still set. So at this point now, B is going to be 1 because it hasn't been addressed earlier. But look at this, both A, B, and C are ready to run. So who's going to run? A. All right. During this time, then we reset A over here to 0 because it's running. C still hasn't had a chance to run yet, so it's going to be 1. And at the beginning of this, yeah, B hasn't run yet, and C hasn't run yet. And so now at this point in time, who gets to run? A, B, and C are able to run. So A, look at this. It's A. A has been addressed and is running, so that's set to 0. B is still not able to run. C is still not able to run. A, and during this time, now A, B, and C able to run. Now at this point in time, this is still 1. Actually, it will start to run. It'll be set to 1, and then it'll be reset to 0 as it starts to run. So this, again, will be A. And in fact, it just turns out that everybody wants a chance to run, but A he starts to hog everything. Can you believe him? That's just not fair. Again, this is version A. Easy enough? If you did version B, it will appear a little bit different. In this case, C will start to run, and then B will run, and then C will run, and then B will run, and then C will run, and then B will run, and that'll continue on and on and on. And so, in both of these examples, what do you notice about the processor? It's overloaded. So you never know when I might give another problem that looks just like this, where the processor is not overloaded. In fact, where the processor might have, it might be the other way around. It's 2.5 milliseconds for a timer tick, and each task takes 1.0 milliseconds. You never know when something like that will happen. For a quiz, perhaps. All right? That is it for this demo. Thank you very much. We can stop the recording.